Hello again and welcome. Today I'd like to spend some time going over my latest software. The new software is going to be called Solver64. It is a Windows 10 64-bit application. It was created using LabView 2020 version 20.0.1 F1. The new software will require the 64-bit runtime along with the NIVSA. I've been testing this new software with the LiteVNA as well as the V2Plus4. Older products like my original NanoVNA as well as my H4 are not going to be supported. Of course, these older devices use a different serial protocol than the newer devices. If products are developed that support the newer protocol, the software of course would support them as well. One person in particular seems to be developing all the firmware for the LiteVNA. They go by the name of Dislord. I've been following their efforts fairly closely, and they've added quite a few features to this LiteVNA that the V2Plus4 does not support. As I understand it, the V2Plus4 is a locked architecture, which basically prevents them from creating newer firmware for the V2Plus4. Of course, if you go to my GitHub account, I have released software that supports the V2Plus4, and of course that software supports the LiteVNA as well. From my own testing, the only real problem I ran into is that as I run the light at lower frequencies, the sweep rate is quite a bit slower than what the V2Plus4 is, and essentially what would happen is my software will time out with an error. Now, of course, if you were using the light above a megahertz, which I'm assuming most people are, you would probably never see that problem. For those of you that are familiar with the release software, Solver64 does not use the same calibration files, nor does it use the same defaults file, so you'll have to generate all that from scratch. Solver64 has quite a few additional features, and again, a lot of those features are only supported by the LiteVNA. So for this video, we'll be using the LiteVNA rather than the V2Plus4. For the few of you who are looking for me to do a review for the LiteVNA, this is probably about as close as we're going to get. So let me go ahead and set this thing up and we can get started. I purchased this book recently. I mentioned it during one of my videos. It's written by Bonaguide and Jarvis. I'd say if you're new to VNAs and you're wanting to learn more about them, this is a pretty good book. I thought what I could do is use this as a reference while we're going through making this video. I thought my friend Flipper would find this interesting. In chapter 1, where they're talking about what is a vector network analyzer, we'll notice this last sentence. They now have the ability to measure and display many other things and are often used in high-speed digital design. So the very first feature I'd like to demonstrate with Solver64 is its ability to reflash the VNAs. That feature supports both the Lite as well as the V2Plus4. So to use that feature, the first thing we have to do is place the VNA into the programming mode. And the way that we do that is we're going to hold down the jog button and then we turn on the unit. And you can see the display stays black. That's normal. You could hear that it did connect. So let's go ahead and we'll launch the software. And again, the software is going to be looking for its default setup file. Now, of course, I already have a file created, but the very first time you set up the software, you won't have this file. So it's up to you to create it. This is looking at the main menu of the software. Let's go ahead and select Link. And you can see it's reporting firmware 255.0. This tells us that the VNA is indeed in the programming mode. Now we select the Setup Diagnostics and we'll go to VNA Flash Programmer. Here we can select the file that we want to program into the VNA. And you can see we have a file dated 2/25 of 2022. This is the most recent firmware for the LiteVNA. Let's just go ahead and select that. And now we can select the Program VNA button. You can see it's prompting us to make sure that we have the VNA in the DFU mode. You can go ahead and select OK. This gives us a status of where we are in the programming. In the upper right, this is the number of bytes that the file contains. This light designates that the VNA is in the bootloader. We send down the reset. That causes the VNA to disconnect from the PC. It then reconnects. So if we deselect the link button, and now we'll reselect it, you can see the software now reports that it's Protocol 1, Firmware 2.2. If we go ahead and select the version, you can see it reports it's the LiteVNA Firmware version 1.2. Build time February 25th of 2022. You can see it also reports that it has the floating point unit. This one is showing a battery voltage of 4.22 volts. So that brings me to the first problem that we ran into with the LiteVNA. Clipper and I both bought one of these from the same company. As a matter of fact, they were ordered at the same time, delivered at the same time, in the same package. And this one here, I've not had any problems with. But when he attaches his to his PC, it had a lot of noise. If you're sweeping between 10 kilohertz and 100 megahertz, I think his VNA with nothing attached to the inputs shows about 60 dB. This one shows about 80, so we lost about 20 dB. So we did quite a bit of testing, and it appeared that the noise is actually being generated inside of the VNA. In other words, any filtering that we did on the USB cable had no effect. As it turns out, it behaves like the V2Plus4. Basically, the designers just didn't consider the worst case voltages for the USB bus, and what ends up happening, as I understand it, is the voltage is too high. It causes the boost converter to put out some noise that gets passed through the IF stages. So essentially what we end up doing is running his from a powered hub, and then we powered the hub from an external power supply that was adjustable. We brought the voltage down a little bit, and sure enough, all that noise cleared right up. Several of the changes that I've made to Solver64 pertain to how the unit is calibrated. Here you can see I don't have anything attached to the VNA other than the two cables. Looking at the main menu, you can see no calibration has been selected. It's currently sweeping between 10 kilohertz and 50 megahertz. And if we look at the Smith chart, you can see we're starting off at an open, and then it moves clockwise around to, looks like J35 or so. In the previous versions of software, I didn't allow for the port extension to be adjusted unless the unit had been calibrated. That's no longer the case. We can go ahead and make that setting anytime we want. Let's just go ahead and enter 1000. And you can see now that's moved us over to roughly J70. Let's try going a little further, maybe 2000, about 3000. It's fairly close now to being matched. Again, the whole idea of this port extension is that we can make adjustments for where we've set our reference plane. Of course, for our homemade standards, our reference plane would be at the end of the open, for example. 2.2, where we're looking at measurement errors in the real world. Here they show the ideal model for VNA. Notice they're referring to the reference plane or the calibration plane. So notice in figure 2.2c, the additional introduction of the reference plane, sometimes called the calibration plane. All error correction is performed relative to this plane. So it is important, particularly in microwave frequencies, to understand exactly where this plane is defined with respect to the coaxial connectors. Again, what we're doing with these error models is we're compensating for every error that's in front of the reference plane, not beyond it. So let's just go ahead and we'll load up a calibration. Again, we do that by selecting 2-port cal. And in this case, we'll load up a previously stored one. And the one I'm loading is called Lite. And this is 401 data points. It's starting at 10 kilohertz. It's going up to 50 megahertz. It's a 1-port Solt cal. And we can see the unit has now been calibrated. Now let's change our port extension back to 0. And we can see there's a little bit of rotation here off of 0. And again, that's because we have not installed our open. Again, I always use the ideal model for all these demonstrations. And you can see here we have a dot basically at 0. What we're going to do now is just insert this small piece of coax. This is just an extension. You can see one end we have a male, the other end it's a female. And you can see now we're back up to roughly J100 or so. Now again, we can compensate for this additional piece of coax by changing our reference plane. Let's go ahead and do that. As a matter of fact, so I'd say this is roughly a foot, and it's going to be about 500 picoseconds for 3 inches. So we need to set this at, let's say, about 2000 picoseconds. A little bit too much. Let's try about 1800. Still a little much. Let's try 1500. That looks pretty good. So let's leave this piece of coax attached. And now let's insert our 20 dB attenuator. And you can see on the Smith chart we're displaying roughly 50 ohms. Let's go ahead and select transmission rectangular. And let's enable our phase display. Well, and you can see it's very close to 0 degrees. Of course, we could trim this in a little tighter. Let's go ahead and set this back to 0. And of course, that phase should be off quite a bit. Sure enough, you can see it's about 20 degrees off. And again, that's because we've added this length of coax here. Let's just go ahead and remove that. And now we're back to 0 degrees across the entire sweep range. Let's type in a negative 1500. And you can see we're back to a negative 20 degrees. Again, simulating the addition of this 12 or so inches of coax. So somebody had written me that some software that's available for these VNAs didn't take into account the travel distance for the two ports. And my response to them is, you know, the original software prior to this, I believe the port extension only affected S11 and S22, not S21 or S12. And so my software, I would say, was even worse. So of course I've gone ahead and addressed that with this software. And of course I handled the 2x factor difference between the two ports. Alright, so off to my right you can see I have our transfer relay out. This box contains the standards that were supplied with the V2Plus4. Here we have our homemade standards. I have a 10 dB Midwest microwave attenuator. Here you can see with the adapters inserted, the overall length of this is basically the same as what our homemade standards are. And of course we have our T-check. One of the problems with the original software, when you calibrate without the transfer relay, it actually measures the through device 2 times. And with the Solver64, I no longer perform that second through measurement. Another problem that I've addressed with the new software, when you select the advanced mode and select the 2-port plot, with the older software the VNA had to be calibrated in order to display the data. That's no longer the case. In the older software there was an LED that told you that the transfer relay was selected. That's been removed. If we select Setup Diagnostics and then we select the Calibration Terms tab, when we look at the calibration standards, you'll notice that there's a value of 1.0 e to the minus 9. Somebody wrote me one time where they had entered in all their own values for these, and they told me how the VNA stopped working. I think they said it stopped displaying data. They had zeroed out this coefficient. Of course, if you look at the math behind this, it causes it to divide by 0. So the whole reason that I've got this 1e to the minus 9 in here was to avoid that divide by 0. With the new software, I add a small offset so we can actually change this to 0 now. Then we can select Save Settings. And just an FYI, that offset is 1e to the minus 99. If we kind of scroll through and look at the other standards, you'll see that C0 is always defined. So if somebody sends you information now that shows C00, you can just go ahead and enter that. It's not going to cause a problem. Again, one of the things I'd like to be clear about is all the data that I've ever shown with these low-cost VNAs, I've used the IDEO model, and that's what I'm showing here. Somebody recently posted up on EEVBlog how they're looking to have somebody characterize some of these standards. You could certainly do that. In that person's particular case, they have a transfer relay, and they had shown some data with that, and I'm going to share that with you. But I think that the problems that they're seeing is something that's going to be improved a whole lot by characterizing their standards. So let me just pop up the data that they've shown, and you can see they are running my software, and they have a mini circuits VAT15. This is a 15 dB attenuator, and they're sweeping between 10 megahertz and 6.4 gigahertz, so they're using the LiteVNA. You can see it gets as low as 16.6 and it's as high as 13.7 dB. And this is looking at the data sheet for mini circuits for the VAT15 Plus. You can see they've specified the frequency range from DC to 6 gigahertz. The nominal attenuation is 15 plus or minus 0.3 dB. For DC to 3 gigahertz, it's going to be typically plus or minus 0.2 dB. And then 3 to 6 gigahertz, they're typically 0.3 dB. So if we talk about 15 dB plus or minus 0.3 dB, you can see it looks quite a bit worse than what the manufacturer claims. Now again, they have a transfer relay installed. So they're going to have cabling, connectors. Of course, they're using their own standards as well. So a lot of things could be going wrong with their setup. I've tried to explain to them to divide the problem down. Just start with a very simple setup. Maybe just do it with a single cable and kind of work your way through it. It helps a lot if you're trying to measure things that you know what they are. I want to be clear that calibration is not a panacea. This is looking at section 1.3.2. Engineers inexperienced with the use of the VNA commonly try to use low-cost, low-quality cables with the expectation that the VNA will remove any performance issues related to these interconnects. The fallacy with this lies that poor quality cables and interconnections rarely show systematic performance. So for this first experiment, we'll be using our homemade standards to calibrate the VNA. We'll program a start frequency of 50 kilohertz and a stop frequency of 1.5 gigahertz. And you can see our VNA is displaying roughly minus 80 dB. That's pretty common for this VNA. Now what I'll do is insert our through standard. And then in the software, we'll select reference, and then we're going to normalize the data. And as we can see, the magnitude is basically 0 now. And if we look at the phase, that's 0 degrees as well. So now let's replace the through with our 20 dB attenuator. And you can see with normalization, at 50 kilohertz, it's reading 20.01 dB. Of course, as we move up in frequency to 1.5 gigahertz, it gets all the way up to 17.8 dB. But let's turn off the normalization. And now you can see how the phase wraps around. And you can see we're all the way down at minus 23 dB, all the way up to 21. So I guess the question is the error the attenuator? Maybe it's in our calibration or our normalization. This is on page 30 of our book. Normalization is better than no calibration at all, but will generally exhibit much more ripple. What we're going to do is insert our T-check next. Again, this T-check is made out of the same material as our calibration standards. You can see it uses the exact same connectors. This is basically, again, just two 100 ohm resistors in parallel. So of course this would read 50 ohms if you looked at the center conductor to ground. Alright, what I'm going to do now is perform the T-check. The software says that the 12-term error model is not valid. There's no transfer relay, or the unit hasn't fully been 2-port calibrated. We're going to go ahead and select continue. And you can see this is not very good at all. Again, if we're looking at the vertical axis, this is in percentage. According to Rohde-Schwarz, anything below 10% is very good. Between 10 and 15% is fair. And anything greater than 15% is a poor calibration. So even at 50 kilohertz, this calibration isn't any good. So the next thing I'd like to do is run a full 2-port calibration. And the way that we would do that is install a short open and load on port 1 and then again on port 2, and then we would install the through between the 2 ports. I'm not going to make you sit through that, so we already have the calibration performed. So we just select 2-port cal, we select old, we'll go to calibration, and we're going to select this 50 kilohertz to 1.5 gigahertz 2-port cal. And you can see it's now been calibrated. Next, what we're going to do is rerun the T-check. But what I'd like you to notice is this 12-term LED right here. And you can see how that illuminates. So the software now has a 12-term model built into it. It didn't used to have that. As you can see, as we move up in frequency, it's actually quite stable now, very close to 100%. Looks like we get as high as about maybe 107% or so. And again, that Rohde-Schwarz paper says anything below 10% of error, all the way from here, all the way down to the bottom of the screen, would be considered a good calibration. So we can be confident in this calibration. Again, I want to be very clear that we're just using the ideal model. So now I have our 10 dB Midwest microwave attenuator. I'll attach that to our transfer relay. Now we'll select transmission rectangular, and you can see we're reading basically between 10.2 and I'd say maybe 9.9. It's very flat. This particular attenuator is good all the way up to 18 gigahertz that they specify it for. This is looking at the data sheet for this particular part. This is a 10 dB part, so this is rated for plus or minus 0.5 dB, so at least up to 1.5 gigahertz. This device is well within the manufacturer's rating. So let's go ahead and we'll disable our calibration. We do that by selecting 2-port cal, and we'll select cancel. You can see the calibrated LED is turned off. I'm going to change our start frequency to 1 megahertz, and I'll change our stop frequency to 6.4 gigahertz. And let's go ahead and we'll run a sweep. Let's turn off the phase. Again, this is supposed to be a 10 dB part, and you can see it's all the way up to about 8.6. It's as low as 15.2 or so dB. So again, is this a problem with the attenuator, or maybe it's just our lack of calibration? So what I'm going to do now is go ahead and calibrate the unit using the standards that were supplied with the V2 Plus. Again, what's unique about this particular set of standards is I've replaced the original load, which is this device here. I've never used that with this part for mini circuits. This is an ANI. I had characterized a set of 7 of these that I purchased. This was the second best part out of the group of 7. Now, of course, we're working at a much higher frequency, so to run through the calibration with these, I have to use the torque wrench. And of course, these have already all been torqued. So let me just go ahead and I'm going to load that calibration. Again, this is looking at our calibration standards that were supplied with the V2Plus4. This is looking at the short, and you'll notice it's been slightly modified. This allows me to use a second wrench to hold that center pin stable while I go ahead and torque it. Again, I want to refer to our book. This is on page 22. Align the male connector with the female and turn only the nut on the male connector, never the body of the female connector. When you turn the nut, the male pin remains stationary with respect to the female receptacle throughout the connection process. Again, you never want to have that center pin rotating inside of the mating connector. The book goes on to say, if you make the mistake of turning the body, the female receptacle rotates with respect to the male pin. Once contact is initially made, this rotating motion will scrape the gold plating off of the pin or the end of the receptacle, or both, leading to excessive wear, intermittent or poorly repeatable electrical performance, and drastically shorten the service life. This is by far the most common newbie error. Also, get into the habit of using the proper torque wrench for your connector type every time you make a connection. Of course, when I'm demonstrating these nanos, you don't see me using the torque wrench every time. Again, below about a gigahertz, I don't always use it, but as I start to work above that, you'll see me frequently pull it out. This habit will serve you well towards the goal of achieving better measurement repeatability. So again, we select 2-port cal, old, and 1 megahertz to 6.4 gigahertz 2-port cal. So let's just right click on the scaling. We'll select auto scale, it'll turn it off. And if we look at 10.5 dB, that's roughly here, and we kind of go across. You can see like maybe around here at about 5 gigahertz, we start to fall out of bounds a little bit, but basically it's very close. Even all the way up at 6.4 gigahertz, we're almost inside the manufacturer's specifications. Now again, let's compare that with our friend's 15 dB. I mean, we're talking 1.6 dB out, so not even close. So again, I think in their particular case, there's something wrong with their setup. Maybe it's their transfer relay cabling, who knows. It's really up to them to sort through it. The LiteVNA increased the number of data points to 1,024, I believe. I've changed this now to support up to 2,048 data points. We'll go to transmission rectangular. You can go ahead and select 1,024 points. Of course, I still support segmented sweeping as well. Recently, I made a short video showing how the averaging works. Again, this is a new feature. We can just enable that, and you can see in the top of the screen, it shows the current number of averages. This is a round robin type average. So for an average of 10, for example, that means the software will store 10 individual sweeps. So as it's collecting a new one, it's throwing off the oldest and averaging the most recent. Of course, it also has this smooth feature, and it also has this max hold. And you can see again, if we turn off the averages, you can see now how our noise level is increasing. The software also supports the firmware averaging, and that's done with this button here. You can see I currently have this set to 1. Whatever you change this to, when you hit the save setup, it'll save it to the defaults file, so the next time you load up the software, it'll automatically set the averages. Another way to set the averages is right off the main panel, and that's using this IF bandwidth. This is a pull down menu. The way the firmware works is he has 4 different bands assigned. Each band has its own unique IF filter. So for example, the very first selection, or an average of 1, gives you a IF bandwidth of 4 kilohertz for anything greater than 100 megahertz. For 400 kilohertz to 100 megahertz, it's 4 kilohertz. 20 kilohertz to 400 kilohertz, it's 800 hertz. And less than 20 kilohertz, it's 400 hertz. So if we want to tighten this down, we can just select it here. This would be 10 averages. Let's go ahead and we'll select store. And now let's change that back. And you can see, just looking at the menu here, we're sweeping, of course, above 100 megahertz. So we've changed the IF bandwidth from 4 kilohertz down to 400 hertz. That should provide us with roughly a 10 dB decrease in noise. And you can see we're pretty close to that. So if we go back to the setup diagnostic page, you can see these 2 additional registers, E0 and E1. E0 is used for any frequencies below 100 megahertz, and E1 is currently anything above 100 megahertz. Let's just select the description and tip. And these are the equations for the different IF bandwidth. Here I'm calling it RBW. That's not really correct. I had asked Disklord about changing that possibly, so he's agreed to that. Resolution bandwidth would be typically associated with a spectrum analyzer, not a network analyzer. Anyway, so for below 20 kilohertz, for example, we take 6 kilohertz and we divide that by E0 multiplied by the average. So it's going to take whatever is in this E0 register, multiply that by the number of averages that you have here, divide that into 6,000, and that gives you your IF bandwidth. So this is my V2Plus4. One of the main problems I had with this is that we could no longer do narrowband measurements. And with the original NanoVNA, I had written some software that would allow me to use this little test jig here to characterize crystals. I show how to make this in my manual, but this is nothing more than 2 3 dB attenuators, and then I have 2 transformers. These are a 4-to-1 transformer that basically help match the impedance of the crystal. Then I made up various standards. This is just a series of capacitors. These range from 1 picofarad up to 100 picofarads, and basically after I calibrate the instrument, I can attach these capacitors and basically do a sanity check. Normally you would just insert your crystal here. So when I first received the LiteVNA, I tried to make the same narrowband measurements and found out that I couldn't as well. So after talking with the firmware developer, they were explaining that if we use the filter, we can make narrowband measurements. So I tried it with a couple of different filters. You may remember this one from a previous video. This was a 12 megahertz 10-pole crystal filter. That's kind of what it looks like on the inside. So I characterized this particular filter on various network analyzers. I stored the touchstone files and then I've uploaded them. And here I'm using the Metis freeware software to view those touchstone files. In this particular set of plots, the black trace is my original NanoVNA, and the red trace is the V2Plus4. The black trace is pretty close to what we would expect, but notice all these images with the V2Plus4. And this is the reason I could never use the V2Plus4 to measure crystals. Notice also that the amplitude is a little off. Here I'm comparing the original NanoVNA, which is in red, against the LiteVNA, which is in black. And you'll notice there's quite a few more data points, of course, with the LiteVNA than what the original Nano has. But notice that the peak amplitude is very close. You'll also notice the side lobe is very similar. Up in this range, the phase is fairly close between the 2 network analyzers. Of course, as we get down into this area, they're both quite noisy, so of course there's quite a bit of error in the phase. In this set of plots, I've got my Agilent PNA as well as my old HP 3589A, and we're comparing them against the LiteVNA as well as the original NanoVNA. So the original NanoVNA, of course, is in orange. The LiteVNA is in red. The HB3589A is brown, and the PNA is in black. Again, you'll notice that the peak height on all four network analyzers, very similar. Notice this falling skirt. Also notice the phase. The LiteVNA is very close to my two bench network analyzers. Another feature of Metis is it allows you to normalize the data. So here I'm comparing my Agilent PNA against the LiteVNA. So what I've done is I've normalized the data to trace one, which is the Agilent. And then what we're doing is we're looking at the deviation. So again, you can just imagine what the filter looks like going up, flat, and then dropping back down. So of course, as we get down into the noise level, the amount of error goes up. And as we reach towards the peak, the error goes down. So again, this particular filter has a bandpass of 1.5 kilohertz. So if we look at that area, these two network analyzers are well within 1 dB of each other. So I'm glad the Dislord's been taking the time to talk to me about some of this. It certainly makes this network analyzer more useful for the hobbyist. Again, the protocol that this uses is quite a bit different than what the Lite and the V2Plus4 uses. This thing can send up, I believe, 101 data points in a second, but that's only for one channel. I believe this thing could send up data at 400 points in a second, but again, you're receiving both channels. Now, the Lite is very similar to the V2Plus4 in that it sends up both channels as well. Again, these two use the same protocol. This was a little faster. I want to say that we had this thing running at maybe 600 samples a second or something. There was a member up on the EEVBlog. They were trying to use the VNA with a couple of antennas to basically set up a radar system, and I believe they were trying to measure their respiratory as well as their heart rates, basically just looking at the reflection from the body. So when the Lite was released, again, I started talking with Dislord about this in detail, and I had asked him, why is it that these are so slow? Is it something about the sweep rate? Is it the actual USB bus? Maybe it's the communication library for the USB? I didn't know, and that's when he talked to me about adding that E0 and E1 register. Again, those are changing the number of averages, which are affecting the IF bandwidth. So by changing those two registers, we can speed this up quite a bit. But early on, I think he had told me that the software that he was using was actually preventing him from going any faster. Of course, my PC is pretty old, but it's certainly going to outpace anything that this is going to do. So I just assumed that he was using Saver. So last Friday, I went ahead and downloaded the latest version of NanoVNA Saver. And to be clear, I've never tried that software before, except early on. I don't even remember at the time if that thing could plot the data. I mean, it was very early. I think all it could do was basically connect to the original Nano. Anyway, so I thought what we would do is just start this thing up and then see how it performs. So let's go ahead and we'll turn on the LiteVNA. Again, you can see I just have our attenuator attached. Pops up a command window. And it looks like this is their main menu. See one difference right now, they have 3 markers where I only have 2, so I would say that's probably a benefit. This is nice. The original QT software, just to select the port, their software would hang, so this doesn't apparently have that issue. Let's just go ahead and select connect. No problem at all. You can see it's gone to the USB mode. And notice S21 gain. So it's roughly 23 dB down. I could believe that. Again, it's a 20 dB attenuator. Let's just change our start frequency to 150 meg. And it doesn't look like it's updating. Let's hit sweep. So it's like you have to give it a single shot. Let's go under sweep settings. And I guess we select continuous sweep. Although it doesn't seem to be updating. There's not an OK button. What's this set band do? Looks like it's reprogrammed our start and stop. 22. Oh, I bet you this is for the amateur radio guys. Yeah, so 80 meters, that's going to be 3 point some odd megahertz. Yeah. Yep, and see if we hit set band. Yep. Okay, so let's just go ahead and exit out of this. Now let's hit sweep. Oh, okay, so now it's going to auto sweep. Let's hit stop again. We'll change this back to 150 megahertz. And again, we'll go to 300 meg. And now let's select sweep. And you can see it's sweeping at roughly once a second. I don't see where. Oh, this is only scanning 101 data points. That's it. This is basically running at the same speed that we could get the data out of the original Nano. Let's see if there's a way to change that. So maybe display setup. Calibration. Don't see anything there. I don't know what manage does. Oh, right here. Number of data points. Let's just set this to, oh, we can't do like 401. I wonder what the significance of this is. 11, 51, 101, 201, 301, 501. I would have thought, because this defaults to 401 data points, or just let me set it. I don't know why this is locked like this. Alright, so we'll just leave this at 101 data points, I guess. It's fine. One of the things I should mention, the reason that I'm running this at 150 megahertz, again, the device has two synthesizers. If you're running the lower frequency synthesizer, it slows down the sweep rate quite a bit. And again, remember that IF bandwidth filter he's got in there. So the lower the frequency that you're looking at, the longer the sweep rate. So with this, I don't really see a way to speed this up. Unfortunately, of course, if you were tuning a filter and you're only seeing an update once a second, that's going to be pretty rough. What's under analysis? Oh. I guess these are some kind of auto test. Unfortunately, I don't see a way to change those debug registers. What we can do, I guess, is exit out of this. And let's go ahead and fire up Solver64. And we'll select our defaults. And let's go ahead and hit link. And we can select sweep. And we'll program the start and stop. And let's just change this to 101 data points. I mean, look at the difference in the speed. Let's select the transmission rectangular. I mean, you can see this is quite a bit faster. Let's go ahead and select the diagnostics. So you can see it's updating at about 180 milliseconds. Now again, we can speed this up by changing this E1 register. Let's go ahead and set this to 1. And you can see our sweep time now is about 40 milliseconds or so. Now let's go back to main. Now let's go ahead and exit. And what I want to do now is rerun their saver software. And again, let's go ahead and hit connect. And we'll set our sweep settings again. And continuous sweep. And exit. And sweep. Whew. You can see it's a little faster, but it's nowhere near as fast as what LabView is. I think this is what Dislord was trying to tell me, is that I think he was concerned that LabView would have a difficult time keeping up with this, probably because of what he was seeing with the software. This is pretty interesting. I would have thought that this software would easily outpace what I'm doing with LabView. Alright, let's go ahead and close this back down, and we'll bring Solver64 back up. Let's set our E1 register to 1. You can see our sweep time right now is roughly 306 milliseconds. And now let's select CW mode. Let's just change this to 200 meg. So one of the new features of the software again is it allows you to change the axes. So we're only looking at one frequency. You just see a little spike off on the left. What we can do is change the axes from frequency to the data points. We do that by selecting X axes. So now you can see we're looking at sample 0 up to sample 800. Again, we've selected 801 samples. Let's go ahead and drop this back down to 101. Let's turn on the min-max. Let's hit our averages. Let's just change our averages to 100. There's 50. There's 100 right there. Again, this thing is holding 100 different sweeps all in memory. It's kicking out the oldest and it's taking the average of the most recent 100. So that's 100 times 101 data points right now that it's rifling through. Let's take a look at the diagnostics, and you can see it's taking about 40 milliseconds. There's two different error statuses for the FIFOs. One of them is for the sampling FIFO, the other is for the display FIFO. So the way the software works is it has one thread that's just basically collecting the data off of the Nano. It then forms a packet or a whole sweep. Once it has that, it loads that into another FIFO, which gets passed off to the main thread, and then the main thread plots the data. So if, for example, the display were to slow down, it's possible that it would overflow this display FIFO. Likewise, if that were to slow down, it's very possible that the sampling FIFO could also overflow. The fact that we're not seeing those turn on, there's no issue with the software keeping up at this rate. Let's go ahead and adjust this down a little bit. We'll go to 50. Let's just reset our averages. Watch that counter. Right there you are. And that was 100 samples right there. Let's try going even faster. Let's try 25. Right there you can see it can't keep up. Now again, we could change that E1 register. That'd certainly throttle it. Let's just bump it up a little bit. Boy, we're right on the edge right there. So let's go back to 101 data points, and we'll select again CW mode at 200 megahertz. And again, we can see this is collecting data at roughly 20 milliseconds. And 20 milliseconds at 101 data points is roughly 5 kilohertz. So currently I have my old HP 33120A ARB. It's attached to my old Marconi RF generator, and I'm going to be using that for a modulation source. So we're currently sweeping between 150 megahertz and 300 megahertz, and we can see this spur. Let's just go ahead and set the peak to the current, and we can see our A cursor is set at 199.875 megahertz. That is our RF generator. Let's go ahead and select the CW mode, and let's go ahead again and select the X-axis so we can see the data points. Now I'll go ahead and select the modulation source, and you can see our ARB is currently putting out a sine wave. This is at 3 hertz. Here I've changed it to 1 hertz. This is at 10 hertz. Here we are at 100 hertz. Let's just change that to a square. Here's a triangle. Here's a ramp. So here's a kilohertz. Let's just take it to 2.5. Let's go ahead and we'll select one of the ARB functions. We'll use the cardiac. Again, this is built into the ARB. And let's change our frequency. And here are our cardiac signals. Let's go ahead and record some of this data to disk. And we'll select CW, and we'll just use the default to record. Now, one of the problems that you can run into if you have a lot of background processing, maybe you're playing a game or something, you can enable this warp function. What that does is it turns off all the foreground processing. So essentially anything that's plotting, the TDR measurements, of course that's being done up here, that's live. Basically that gives as much priority as possible to data collection and recording. Let's go ahead and select that. We can turn it back off. Let's go ahead and we'll select the ramp. And now we can turn off the record. And now we can go ahead and post-process that data. We do that by selecting Advanced. So notice that the menuing here has changed a little bit. So now when we select post-processing, you can see this is where the 3D surface analysis is at, as well as our histogram and our scatter plots. So the person that was doing the heart rate monitor, he was attempting to understand the binary file format that this software uses, and I ended up writing him a little program that converts that to CSV. What I've done now is I've added that to this menu, so you just select binary to CSV, and we can select record.bin, for example. Now if we go to our CW directory, you can see we have this CSV file. Again, that can be read by most software, including Excel. Let's just go ahead and load that file up. We do that by selecting Add Waveform, and we select record.bin. And let's go ahead and zoom into this a little bit. And here we can see our heart rate. And of course we can scan through this data. And here we've converted over to the ramp. You'll notice that there's no missing data. Another thing we can do with this is display it in 3D. And again, to be clear, you have to select the zero span or CW mode to display this data. This software also has the ability to play this back. Of course, we can adjust the volume. Let's select a different waveform. And again, let's look at the two-dimensional view of it. You'll notice in this data set we have a chirp. So you can see at 5 kilohertz it's actually possible to process audio with this software. Let's reload our original data set and we'll go back to sequence. What we can do now is select slice. Let's go ahead and we'll change the number of samples from 1,000 to about 100. This allows us to change the trigger level. So this is basically every one of those ramps overlaid on top of each other. As you can see, as I change the threshold, here's our heartbeat. Of course, the pre-trigger sets the number of samples prior to the triggered event. If we change that to 100, for example, it just gives us more data on the front end. There was an error with the older versions of the software when importing the stream data. It would cause an overrun fault. I've gone ahead and addressed that with this version of software. I have a little transistor radio out. Let's just go ahead and turn this on. So what I've done is I've hooked an antenna up to port 2. As you can see in the software, I'm sweeping between 1.3 meg and 1.5. I'm just going to go ahead and select CW. And again, we'll select record. And then we'll go ahead and call this radio. Oh yeah, I can see the audio right there. Should be good enough. We should be able to tell if we can decode anything. We'll go ahead and stop the recording, stop the sweeping, and again we'll go to Advanced and we'll add our radio file. Just looks like a lot of noise. Let's go ahead and select 2D. I think there's something there. Let's try to zoom in on this a little bit. Yeah, I'm thinking that's audio. Go to audio settings. This should be somewhere around, we said 5 kilohertz. Let's just adjust it down a tad. And let's try playing this back. It's definitely in there. Yeah, it doesn't make a very good radio, but it is interesting that it's fast enough to decode that directly. It's pretty impressive. Again, I think the advantage to something like this would be if you are trying to set up some type of a radar experiment and then you're modulating that signal, obviously with the ability for this thing to sample faster, opens up the doors as far as what type of signals that you'd want to measure. So yeah, I'm pretty impressed with this feature. At the start of the video, I had mentioned my friend Flipper had bought 2 of these LiteVNAs. For some reason, his had much higher noise than what mine did. He ended up buying a second one to replace it, and then we discovered that the second one exhibits the same high noise as his original one. So this is the last one he purchased. So I asked on the forums if anybody else had seen this problem, and I guess that caused the developers to post up on the LiteVNA group IO. This is their post right here. We can see here he's saying, when working with a USB power supply, the voltage of the input DC-DC boost power supply is very close to the voltage of the output, resulting in a very narrow PWM pulse bandwidth. These pulses, man, are the IF, resulting in a large measurement noise. To avoid this interference, the power supply circuit can be modified. Of course, we have the 64, so he's saying remove D1, R7, and R1. The problem that I see is that we don't have the schematics for this, and I really don't know what the implications are making these modifications. So as I had mentioned earlier in the video, what we ended up doing was basically just dropping the voltage to his. So what I'd like to do is just show you the difference between these two. So let's set the start frequency to 9 kilohertz, and we're going to set our stop frequency to 1 megahertz. Now let's select the transmission rectangular, and let's just save this to memory 1. So there is no averaging being done. This is just the raw data. And again, the cables were not connected to anything. These are just floating. So let's have a look at Flipper's unit. Again, we'll reconnect. Again, these both have the same firmware installed. We'll hit sweep, and we'll change the sweep range. And there you have it. Look at the difference. So once we get above about 400 kilohertz, if we look at the average noise, we go from basically about 80 dB up to about 65 or so. So I don't know, maybe it's a tolerancing problem in the design. It's hard to say. Many years ago, I attended a workshop with one of the developers of the USB standard. During that workshop, they had showed the worst case analysis for the power supply voltages that your products need to be able to work with. And I think what's happened here is basically the designers didn't consider that. What we're going to do is just store this to memory 2. Here I have a modified USB cable. What I've done with this is I've slit the outside insulation with an X-Acto knife. I pulled out the ground and the VCC pins. I left the 2 data pins together. Then I resealed the shielding. I've added a silicon diode going from the PC out to the Nano, and then I've inserted a 1000 microfarad capacitor, and again the data lines just run straight through. Again, all I want to do is drop the voltage going to the Nano to try to get it within that working range. So again, I'm just going to install this upstream, and let's go ahead and relink, and let's go ahead and set our start and stop frequencies. Looking at this, it seems like adding that series diode has actually caused Flipper's VNA to get a little lower than my VNA. So it looks like even with my VNA we could gain a little bit of performance by adding that series diode. Again, I want to be clear that I've made no modifications to Flipper's VNA. Basically, he's asking you to remove R1, R7, which is here, as well as D1, which is right here. I don't know if I can zoom in and keep this camera in focus. You can see these parts are very small. So of course we'll be using our micro tweezers for this, and we'll be doing this work under the microscope. So I'll be doing this work off camera. So give me just a second. So to remove these parts, I used a set of mini tweezers. These are made by Pace. I have a couple of different tips for this. This is the finer set that I used, but the parts are so small I end up grinding the tips down on this set. You can see what I've done is I've slid the components over, but they're still soldered to one pad, and that way if I decide to put this board back to the original condition, I still have all the original parts. Right, you can see I have the unit back together. Again, we'll plug it into the same cable. Unfortunately, it looks like it no longer powers up. So I reinstalled our 3 parts. And You see it powers up just fine again. So that's kind of a bust. It looks like there's something maybe going on with the battery with this unit. Looks like it's putting out about 2.56 volts. So this is supposed to be 3.7. I wonder if that battery is just dead. So talking with Flipper, it turns out that the serial number for the very first Nano he had is 3 digits away from the Nano that I have. So that makes sense. Again, those were purchased at the exact same time, same company, shipped at the same time. So I asked him to check to see if his would actually run off the battery. It does. So apparently, because this one was the new one, this never got charged. So I went ahead and put the mods back in. I let this thing sit and try to charge. And after a half an hour, the battery stayed flat. So what I did is I manually tried to charge the battery up using a power supply. So this thing has been charging for about 3 hours now. And you can see, it comes up just fine now. And we'll go ahead and run this without our little dropping cable. Let's go ahead and turn it on. We'll go ahead and link. And let's start the sweep. Let's change our start and stop frequency. It looks like it may be a little bit lower. For all these tests, I've calibrated the VNAs. I ran them in 2 different bands. Basically at the lowest frequency up to 1 megahertz, and then 1 meg to 100 megahertz. We'll be using Metis to display this data. Let's just take a look at the original NanoVNA. With that, we're scanning between 50 kilohertz and 1 meg, and we have 101 data points. Let's compare that with my original light. And you can see my original light is quite a bit noisier than the original NanoVNA. Let's see how that compares with Flipper's. Again, this is before any modifications. Here we can see is we get above 400 kilohertz. This is definitely more noisy. Let's just see how it looks now with the test cable. And you can see it's quite a bit lower. Let's compare that with my light without the cable. You can see with the cable, Flipper's is actually lower noise than what mine is without it. And here we can see the 2 lights using our test cable are actually very similar. Now let's take a look at Flipper's after making the modifications to the power supply. Again, this is removing R1, R7, and D1. And again, just to compare against the original NanoVNA, you can see it's still quite a bit quieter, especially as we get below the 400 kilohertz. This is why I used the original NanoVNA for doing those PDN measurements. This is the original NanoVNA sweeping from 1 meg to 100 megahertz. And here's Flipper's light without any modifications. And here's my light, again with no modifications and no cable. Here we're using the modified cable with Flipper's versus mine without it. And you can see now Flipper's is actually outperforming mine. Again, here's my light with the diode dropping cable compared with Flipper's. Again, both very similar. And again, this is with Flipper's board being modified. So it doesn't appear that there's any benefit to making these modifications to the light. I was having a discussion with Dislord up on EEVBlog. He talks in here about, in the light, if removed DC block capacitor and ESD protection diode, possible get better results on low frequency range, less than 10 megahertz, but a huge increased chance to burn RF switch. I asked him if he had any kind of benchmark data he could present. Sadly, I wasn't able to get any further details from him as far as what kind of performance gains we'd expect, but we were definitely interested in seeing if we could improve the lower frequency band, because that would be very important for making these PDN measurements. So I asked, as far as pulling the blocking capacitor, what was the common mode range, and if P1 source would then be DC coupled. Unfortunately, we don't have the schematics for this, but somebody had posted a picture, and here we can see D3. This is the transient protection diode, and here's our DC blocking capacitor. But you'll notice that feeds right into the IC, so I'm not too concerned about pulling the ESD protection. I think for most EEs, we'll have good lab practices as far as ESD is concerned. But I am a little concerned about just pulling that capacitor out and replacing that with a short. Unfortunately, I never got any answers to that question as well. So I took Flipper's unit back apart, and then I removed the 2 metal cans. This is what it looks like, and this is looking at one of the ports. Here we can see the protection diode. Here's our blocking capacitor. This looks like an attenuator. and then it goes into our switch. First thing I'd like you to notice, this is actually copper up in this area. So there's quite a bit of splatter. I'd wondered if we just clean this thing up, what would that do for our high frequency performance? So what I've done is I've gone ahead and I've removed the 2 transient protection diodes, but I left the 2 DC blocking capacitors in play. Again, this is looking at Metis. This is showing my modified cable with the diode drop. Also shown is where we've removed R1, R7, and D1, and then where I've removed the ESD protection diode. And you can see all 3 of these basically lay right on top of one another. So I don't think there's any further gains as far as removing the protection diode, at least for low frequency. I wouldn't have thought there would be because the capacitance of that should be very low. However, this is looking at before and after pulling that diode. Again, we're sweeping between 150 megahertz and 6.4 gigahertz. And of course, there's no calibration being performed. But notice right here, this dip. This is after modifying the unit. So it looks like there may be some gains, possibly up around 4 gigahertz or so, by removing the diode. I don't know, I'd say it's a little inconclusive. Again, I've taken the time to clean up the circuit board while I had it apart. So this is the same shot after cleaning, so you can see I've removed all this debris. It's possible that just cleaning up the board had that effect. Personally, after playing around with it, I wouldn't recommend that you make any modifications to the light. I think that you're better off just making the modification to your cable like I've done here. One of the big concerns again would be if you could even charge up the battery after these modifications have been made. I wonder too, even with the battery charged up, is the supply after these modifications going to be able to keep up where it can actually keep the battery charged over long periods of use? So I've asked those questions in the forums, and unfortunately the designers never responded. I'm not sure if they just don't know. It's very possible, but I'd recommend that you exercise a little caution before you make those modifications. Again, just modifying a cable like this, you can see we get the exact same performance. When I first received the V2Plus4, one of the things I noticed in the Windows QT software was the ability to program the output synthesizer's power levels. And unfortunately, that's never worked with the V2Plus4. However, with the LiteVNA and Dislord working on the firmware, he's gone ahead and added that feature. So let me just demonstrate how that works. You can see we've set the sweep mode to CW, and we have a center frequency of 10 megahertz. Now let's go to Setup Diagnostics. So in the background here, I have our signal hound. You can see it's also set for 10 megahertz. We're set for 1 dB per division. We have a reference level of minus 10 dB. I have an attenuator in series with the signal hound right now, so this is not an absolute number. Let's go ahead and adjust this down 1 tick. Let's try it again and again. As you can see, we can change that output level. Let's go back to the main. And let's plug in 200 megahertz. We'll go back to Diagnostics. And now on our signal hound, we'll plug in 200. You can see we have quite a bit more range with the ADF. It also appears that the steps are a lot more linear. Now again, whatever you've set these to, when you hit Save Setup, that'll store these values in the defaults file. So when you connect to the LiteVNA, the software is going to initialize it to these 2 values. A couple other changes that I made to the software. There was a bug when importing touchstone files. If you happen to have an empty line inside of your touchstone file, it had a problem with that. I've gone ahead and addressed that. I've also added a feature where you can sweep an antenna to look at its radiation pattern. Again, my software supports these M-drive motors. Obviously, you're going to have to come up with your own rotor system. Of course, you're going to have to come up with the mounts and the mast. You may remember I had the same type of motor driving a linear slide that had an adjustable airline attached to it. So to use this feature, you have to go to the Setup Diagnostics and you're going to select the stage. That's going to tell the software that you have one of these motors attached. Then we can go to Advanced and we can go to Antenna Sweep. Just looking at the main page, and then we can select Sweep. Then assuming that we have 2 antennas, one is a receiver, the other one is the transmitter, we're going to attach those to the 2 ports of the network analyzer, and the software then is going to rotate the antenna and it's going to plot that radiation pattern. You also have the ability to store the data to 1 of 2 memories. That allows you to easily compare changes that you've made to your antenna and how they affect the radiation pattern. I'd use this breadboard to demonstrate using the original NanoVNA to make PDN measurements. You may recall during this demonstration I was using a target impedance of 10 ohms. As part of that demonstration we used the Nano to measure some very low resistance values. What I'd like to do is repeat that experiment with the LiteVNA. Again, to do that we have to break the ground loop between the two ports. Again, these are a coaxial transformer. I made one of these for an SMA, the other one is an N style. You can see they have slightly different properties. We'll be using this one on the left today. I had a few people comment about my not showing the inside of these transformers. If I showed you a transformer and I said, here you go, this is what it looks like, you wouldn't know the difference between these two materials. They look identical. They're not. So of course the material selection is very critical for this transformer. I don't remember how many iterations I went through before I finally settled on this type, but it was quite a few. Here you can see I've got different size cores. This one's quite large, fairly small. They're all wound basically the same. Here you'd have your piece of coax, for example. I mean, all you're going to do is take that coax and start wrapping it around. Once you get about halfway through, you're going to bring it back on itself, like so, and you're going to go back the other direction. Reason we're doing this is we want to have the two ends of the coax feed from opposite ends. Basically, we want to reduce the capacitance between the two. Of course, if you've never seen one of these wound before, I'd just use Google. You know, I mean, they've got the images feature, and you could probably see hundreds of these. But again, for me, this wouldn't be very helpful if somebody showed me this. I'd be asking what the heck's that core made out of. Anyway, so you can see we've got our transformer. You can see that's in series with port 2. So we're going to set our start frequency to 10 kilohertz, and we're going to set our stop frequency for 10 megahertz. So when you're performing a calibration, you can use this averaging as well as the firmware averaging. If you could reduce the noise, maybe you can improve on the calibration. So what we're going to do is select a different IF bandwidth. So normally the light defaults to an average of 2. That would be the second one on the list. Let's adjust this thing down to 4 and let's see how fast it sweeps. Again, it's going to slow down quite a bit. We'll leave this at 401 data points. Let's see how fast it's sweeping. So about 3 seconds right now per sweep. Alright, so we're going to use this setting to perform our calibration. So again, we just select 2-port cal and we select new. We'll be using our homemade standards, and again, I have not characterized these, and we're using the ideal model. So we'll go ahead and install our short and our open and our load and finally our through. And we'll just use our default name. So let's just start with the highest value we have. This is a 1K ohm resistor, and you can see it's reading 1.0 K ohms. Here we have roughly a 500 ohm resistor, and again the return loss on this should be roughly 1.75 dB. This should give us a SWR of 10 to 1. Looks like we're showing roughly 502 ohms of resistance. And if we look at the return loss, we can see 1.74. And let's have a look at the SWR. And of course you can see it's roughly 10 to 1. Here we have a 100 ohm resistor. Again, this should be a return loss of 9.5 dB and a SWR of 2 to 1. Again, we can see the return loss is 9.50, and looking at the standing wave, it's basically 2 to 1. Now let's go to the other end. So this is roughly a 25 ohm resistor, and of course that's also going to give us a return loss of 9.5 dB and an SWR of 2 to 1. And again, we can see the return loss is 9.50, and looking at the SWR, it's basically again 2 to 1. Again, as we start looking at lower value resistors, we're going to change from the shunt configuration to the shunt through. So again, this resistor is essentially from the center conductor to ground, just like what this one is. However, we're going to place this in series between the two ports, and this is where our transformer comes into play. If you're interested in understanding the reason why that is, I suggest you watch that video that I made on the PDN measurements. Alright, so I've changed our start frequency to 30 kilohertz. Basically what ends up happening with the light is you start working at lower frequencies. The data that we get off of this isn't very good. Again, if you look at the back, this unit is rated for 50 kilohertz to 6.3 gigahertz. So even at 30 kilohertz, we're working outside of the range that they rate this thing for. Then we'll be using our Bode plot. You can see it's set to ohms. We're using the blue scale here on the right. See, it's displaying roughly 0.1 ohms. Again, this is a log sweep, so here's 10 kilohertz, 20, and we're starting at 30. So this would be 40, 50, 60, 70, 80, 90, and 100. Of course, this is going to take a fair amount of time to run through, so I'll speed up the video for you. I'd like to point out that we're all the way down to 0.09 ohms, and then we see this step. You'll notice this other little notch. I suspect this is all firmware that's causing that disturbance. Again, my software doesn't really do anything other than display the data. Up in here you can see where the cable has started to go inductive. Let's go ahead and we'll save this to memory 1. And now let's install our 25 milliohm resistor. This is two 50 milliohm resistors in parallel. Again, the trace on the bottom is our 25 milliohm resistor. See, again, it's fairly close. Let's see if we see the same kind of a trend. Notice we do. It's not as pronounced. And again, we can see the inductance of our cables is starting to dominate the measurement. We'll save this to memory 2. Here we have our 1 milliohm standard. This is a 1% part. And of course, here's our 100 milliohm resistor at the bottom, 25 in the center, and 100 at the top. Let's go ahead and turn off M1. Basically allow it to auto scale. We can zoom in a little better. You can see this would be 2 milliohms here. Let's go ahead and save this resistor to memory 1. This is the lowest value standard I made. This is a 100 microohm 1% part. I'm not expecting there to be a whole lot of difference between the 100 microohm and the 1 milliohm. Let's go ahead and select sweep. Let's just turn off our 25 milliohm resistor. So here we're looking at both the 1 milliohm as well as our 100 microohm. You can see they're basically right on top of one another. You can see the darker blue is our 100 microohm. They're starting to deviate a little bit as we get beyond about 300 kilohertz. So you can see there's some differences between these two resistors, but if you go back and look at that video that I made where I initially showed those PDN measurements, the original NanoVNA would definitely outperform the Lite. Currently I have the homemade load standard attached. Looking at the graph, you can see it's definitely not a nice perfect dot in the center of the screen. We're currently sweeping between 50 kilohertz and 6.3 gigahertz. That is the manufacturer's specified working range. So the unit is actually calibrated right now, but of course we've calibrated it using the standards that were supplied with the V2Plus4. Of course, operating at these frequencies, the standards had to be torqued during the calibration process. So what we're going to be doing is attaching our homemade Beatty standard. Again, this is a 50 to 25 to 50 ohm Beatty standard. It's 70 millimeters long. On the back side of this we have an HP terminator with just a few adapters on the front end to get us to the SMA connector. And you can see this is definitely not a nice clean dot at the end. Let's go ahead now and select Advanced. And you can see we have the time domain tab open. Let's just zoom into this a little bit. And here's our cursors. You can see these are off quite a bit. What we can do is select the cursor marker. We'll pull this down slightly, maybe into this area here. This will set the trigger level. You can see the two cursors are now located at the apex of the impulse wave. And as you can see, the full width half height is measuring roughly 71 millimeters. You can select auto scale again to zoom back out. So this is zooming into the area where the two cursors are located. Of course, we can change the filter type as well as the window. So let's go ahead and turn off our calibration. Again, we do that by selecting the 2-port cal, and we'll just select cancel. You can see it looks quite a bit different when we're looking at the Smith chart. Let's go ahead and go back to advanced. You can see it has this definite upward trend to it, but the full width half height is still roughly 70.7. Let's drop this thing down to 101 data points. And again, we'll go back to advanced. And you can see we still have a full width half height of roughly 70.7. I had somebody writing me about this where essentially what they were doing was changing the number of data points, and their claim was that they could get better time precision by reducing the number of data points. Of course, I tried to explain to them numerous times that the time resolution is dictated by the upper frequency of the VNA. This is from page 267, Time Domain Reflectometry and Distance to Fault Measurements. The minimum resolution, or spacing, is determined by the highest measurement frequency. In this case, 20 GHz yields a resolution in low-pass mode of 1 over 20 GHz, which is 50 picoseconds, or 590 mils in air. In the bandpass mode, the formula is 2 divided by f-stop minus f-start. The maximum range or distance that you can measure is determined by the number of points. The maximum range or distance that you can measure is determined by the number of points. In this case, 2,000 points gives a range of 100 nanoseconds or 98 feet in air. To measure longer devices, simply increase the number of points or otherwise decrease the frequency step size. For bandpass or low-pass impulse responses, the unambiguous time or distance is given by the reciprocal of the frequency step size. For a low-pass step response, it is half the value, as example, 50 nanoseconds or 49 feet. Again, if you're new to the VNA, a very good reference guide. Sadly, what I find with this is a lot of people that play with the NanoVNA really don't have the background, and unfortunately they seem unwilling to do their own research. As a matter of fact, for the original software, I had written about a 200-page manual for it. When I do get around to releasing this software, there will be no manual available, and that stems from several of you who have written me private emails requesting for help that was covered in the manual. So I don't see any value in spending any time creating a manual that people just flat out refuse to read. Currently, this software is still not available to the public domain. One of the things I'm going to do is purchase a license for LabView. Again, my own personal license is for 2011. National Instruments does offer the community version of LabView now. Unfortunately, I'd have to hire an attorney to interpret their license agreement. I'm not sure if I can actually use that to release code or not. So my plan is to just go ahead and upgrade my own personal license, and then there won't be any question as far as distribution. So there's a few things left to do with the software. If there's other features you'd like to see demoed, feel free to write. Again, most of the software runs basically the same way as the old does, so the manual, of course, is quite a bit out of sync now, but you can still use that as a reference, and the same thing with the previous videos that I've made. Well, I think that's going to be it for this video. I hope you enjoyed it. Until the next time, stay safe, and we'll see you soon. Later.